I'm Josh. I'm from Celestia. We're the first modular blockchain network. You might have gotten an overview from Evan, who gave a talk earlier this morning. But I'm going to be talking about modular versus monolithic architectures. Just, some context. I'm kind of biased towards the modular architecture for obvious reasons here. And the clarification, what do we mean when we say modular here, right? So it's an overloaded word, as is everything else in crypto. And what we mean when I say modular is it's a modular network architecture and not a modular software architecture. And so we're familiar generally with Cosmos, right? So this would be a modular software architecture. We have the Cosmos SDK state machine, that's your application, and that's going to be talking over your application blockchain interface, your ABCI, to Tendermint. And these are fundamentally different code bases. They can be separate. So that's a modular software architecture. This is not what I'm going to be talking about in this talk. I love Cosmos, but that's not what we're here for. What we're going to be talking about is a modular blockchain architecture. And so just jumping into some examples, when I say monolithic, I'm kind of referring to Ethereum. We'll set it as like Ethereum 1 now, Solana, existing Cosmos chains, and Avalanche. When I'm talking about modular, I'm going to be talking about Celestia plus, a generic execution layer, a Veil from Polygon plus a generic execution layer, or we can say Ethereum 2 plus, I guess, Ethereum 2 again. What are some trade-offs here between having a modular or a monolithic network, right? So if we're in monolithic, the pros, we have a very simple architecture here. Everyone's familiar with it. You're going to have full nodes. You're going to have light clients. Your full nodes execute your transactions. You're going to have some kind of consensus. That's kind of the one model we're going to be looking at here. This can give you a faster time to finality, and that kind of relates to all users being on a level playing field. This is obviously dependent on your desired settlement assurances, but generally there's only going to be one block time. You can't choose to go up and say, okay, I'm going to have a slower settlement time or lower settlement assurance guarantees for a faster settlement time or whatnot. That we'll get into Rollup architectures. We'll go on. Some cons here, it's less scalable, right? We've all discussed, the block wars and block size debate. I'm not going to get into that here, right? But that's kind of our scaling solution. If you want to make the blocks bigger, you can change consensus algorithms, but generally, there's not a lot of room to scale within this architecture. If we go to a modular, we have a much, much broader design space. It's more scalable, or at least has the capacity to be more scalable. And you can have specialized nodes for different purposes. So you can have a block producer node that just produces blocks. You can have a full node that actually receives all the transactions and validates all the transactions. You could just have a data sampling light node that doesn't execute any transactions, but just validates the availability of data within this network. You can also have a light client. This light client can be either trust minimized or trusted, where it's receiving headers, and it can choose to receive those headers from a full node that it trusts, or it can receive these headers and have the capability to either verify a validity proof or to be able to re-execute one transaction by checking for fraud proofs. And the users are able to make trade-offs in what nodes they run depending on the requirements for their safety. If you really are doing large transactions and you want to make sure these are going through and you're verifying everything, you're allowed to run a full node still, same as in a monolithic network. You could also go all the way down and say, I just want to run a light client. I just want to be able to submit my transactions into the network. I'm going to trust a full node that I have. I'm not going to do any validation on it. The cons, obviously, it's more complicated. We have more node types, and it's going to get more complicated than this slide gives it. So what are some architectures we can look at here, right? Just really quickly covering a monolithic network architecture. I think we're all familiar with this. You have a bunch of full nodes in the network. They're going to communicate with each other over peer-to-peer. They're going to get consensus with each other. You're going to have a new block. You're going to have a new block after that. You're going to have a new block after that. You can have a light client. That light client is going to talk to a full node, and it's going to receive some trusted headers from that full node. But it has no means of verifying this. It knows that the header is valid in that it has a Merkle root for it, but it doesn't know that this block actually truthfully followed the state transition rules of the network. Modular network architecture. This is kind of a simple, constructed example here. We could have data availability full nodes, the base layer, right? And these are very, very similar, or really the exact same as a monolithic architecture, in that they're going to be full nodes that validate all transactions. They communicate over peer-to-peer. They get consensus, and they vote. And then you could have an execution node that chooses to just read and write to these full nodes. And then in this simple example, we would say these execution nodes might all be full nodes, where they're reading from this lower layer, and they're choosing to re-execute these transactions. We can also go to a more probably correct roll-up network architecture here, right? So we still have all these data availability full nodes at the bottom here, and I'm not even trying to expand into, I'm not covering Celestia's kind of data availability sampling and light nodes right now. But then if we go up to this middle execution layer, we can be a little more complicated, right? We can choose to have a block producer node, and that's actually going to read and write data into our data availability network down here. We can choose to have a full node. That full node's not going to produce blocks, but it's going to receive blocks from the block producer, and it's going to re-execute the transactions to validate the state transition functions at this execution layer. It can do that not by getting all of the data from the block producer. It could just get a header that informs it that there is a new block, and then it can go read that data from the data availability full node, or a light node or a light client in the data layer, depending on the trust guarantees it wants to make there. Then you can also have a trust minimized light client, and this is something I really want to draw attention to because it's a distinct thing that you don't get in kind of a monolithic architecture. We can have a light client. All this light client is doing is receiving full nodes, or receiving headers from a full node in the network. And the trust guarantee is that you have one honest full node in the network that is re-executing all the transactions of the block producer. And this light client, by receiving those headers and then also reading fraud proofs from the data availability layer, which would be produced presumably by a full node that re-executes these, and I'll go into this a little bit later on a different slide, it can execute this fraud proof and actually get guarantees not just of the validity of the blocks from a Merkle root, it can get guarantees of the actual state transition of the stuff produced by a block producer. So this allows you to have kind of a very centralized block production while having light clients that don't store any large quantity of data, but they're able to have high trust guarantees as long as you have at least one honest full node. And then I'm going to not cover this too much, but we can go up again, right? If people have read Starkware's Fractal Scaling paper or blog post, right, you can have rollups on top of this execution layer here as well. So let's cover the types of nodes we can have in these different systems, right? Like I mentioned, in a monolithic layer, there's not that many different types of nodes. You can have a validator. It's going to download and execute all the transactions. It's going to participate in some kind of consensus process. And it's probably going to, through some leader selection algorithm, produce blocks occasionally, right? You also have full nodes. This is just going to download all the transactions, and it's going to execute all the transactions to validate them, right? And I'm using kind of Tendermint and ABCI style nodes here, right, as an example. A light client, all a light client's going to do is download headers from a full node. And the thing to keep in mind, right, it's downloading the headers, and maybe it's verifying the Merkle root, but it's not sure that these headers are actually valid state transitions. This is just what it's being given by a full node. If we look at modular, we have kind of two layers I'm going to split this into, right? We can have nodes on the data layer, and we have nodes on the execution layer, right? Within the data layer, we're actually going to look relatively similar to our monolithic network, where we have validators that download all the transactions, participate in consensus, and produce blocks. We're going to have full nodes that are going to download all the transactions, but note, we're not necessarily executing the transactions here because in a data layer, you might not have a state transition function here. This is one of the things we are allowed to separate out by having an execution layer above. And then we have light nodes. These light nodes add a new thing that I'm not going to dive into too much, but a lot of Celestia documentation is out there on this about how to perform data availability sampling on transactions. And this just allows us to have light nodes where we can have nodes that store essentially a percentage of the network state. They don't store all of the state like a full node, but they store some of it like a light node, and they allow you to do data availability sampling to give you guarantees of the existence and validity of that data. And then if we're on the execution layer, right, we have block producers. They create blocks and they write blocks to the data layer, right? If we have full nodes, those download and execute all transactions. But the thing to keep in mind, when I say they're executing transactions against the state transition rules of the specific execution layer here, not necessarily state transition rules of a data layer that might also have some of its own state transition rules. It also produces fraud proofs, or it can optionally produce fraud proofs, and we could also add that it could produce, I'm going to leave out validity proof here, but we'll say it can produce fraud proofs because as it downloads and executes all the transactions, it will be able to tell if it got an invalid transaction, and if it gets an invalid transaction, it can choose to generate a fraud proof, broadcast that fraud proof to now we have a trust minimized light client, right? All it has to do is it downloads the headers and verifies these fraud proofs that may be produced by an honest full node in this network, and that makes it trust minimized. So it's going to receive these headers with these Merkle proofs and also have the ability to execute these fraud proofs that it's given so that it doesn't have to trust the full node that to tell it's truthful. It can actually verify these fraud proofs. So rollups, this is kind of like how this has come into play, right? And how we've seen this thing evolve. I'm going to talk briefly about sovereign rollups. They're a little bit distinct from what we might be used to in like Ethereum's L2, L1 space. The key distinction, I think, is that they have no lower level to exit to, right? So we're all familiar with like liveness guarantees of rollups, where if I'm on an L2 and I have a centralized block producer on my L2, and they choose to start censoring all of my transactions, or for whatever reason I can't execute transaction on that layer, I have the ability to have essentially an override exit on the layer 1 below, but that's reliant on the L1 having its own execution layer below it, where I can actually execute a transaction against a smart contract, essentially, right? In a sovereign rollup, we don't have that. We're assuming we just have a data layer, and there's no ability to have a smart contract on that data layer that allows you to have an exit for your tokens here. We're also going to assume that we have trust minimized light clients in here, and that's enabled by the fact that you have a data layer, so you can guarantee there's data availability of these fraud proofs that are generated on the execution layer. There's different types of rollups still within sovereign rollup, right? So optimistic rollups, for those who aren't familiar, we have fraud proofs. They're generated by honest full nodes in the network, and they can be validated by light clients, and the light clients validate these by re-executing a transaction from the state that is given in the fraud proof. When I say given in the fraud proof, it could be a full bundle that is either gossiped over the network, or it's probably written to the data layer, but it can also just tell it where to find it in the data layer. So it doesn't have to like rebundle all of the state and push it to the data layer again. It can just also give it instructions for how to go find it in the existing data in the data layer. This is fundamentally the data availability problem that we're seeking to solve here. So here's kind of a quick run through of what this would look like, right? We have a user, they talk to a block producer. This block producer could be, a single block producer. It could be a decentralized sequencer network, right? But they're going to write a transaction to the block producer. That block producer is going to generate a block. They're going to store the block on Celestia or another data layer, but I'm biased here. They could also gossip this block header to both a full node and a light client in the network. And then that full node in the network would choose to retrieve that block. So instead of being gossiped the whole full node, it's going to retrieve that block from the underlying data layer where it was already written. Then it's going to validate this block. In the scenario where that block had an invalid transaction in it, we're going to have this full node generate a fraud proof, and then it's going to store this fraud proof. That arrow's wrong. That should go to Celestia. It's going to store this fraud proof on Celestia. The light client's going to then retrieve this fraud proof, and then it has the ability to verify the fraud proof, right? And so this is kind of our full scope of how a negative transaction or an invalid transaction would go through this network, where the light client at no point in time had to download or store any part of the block. All it had to do was retrieve the fraud proof, where I'm kind of papering over, retrieve the fraud proof would also get all of the state necessary to re-execute this fraud proof. The other type of rollups, right, are ZK rollups. So these rely on validity proofs. We're going to assume the validity proofs are generated by a prover, and they're verified by nodes, and that's just using math. I'm going to paper over this. I am not a zero-knowledge researcher. I'm not going to dive into Starks versus Snarks. How this would kind of work, right, is we have a user. They're going to send a transaction to the prover. That prover is going to generate a block for this transaction. It's also going to generate a proof. It can then go store the block and store the proof on the data layer. And then any node in the network, I'm not going to distinguish between full nodes or light nodes or light clients. It's just going to retrieve the block and retrieve the proof, and they can verify the proof. Obviously, there's some nuance in that node type there, right? We could choose to just retrieve, headers, and then it could, just retrieve the headers and the proof, and then have the ability to verify the proof, right? But we can see this is a slightly simpler model, right? But we're papering over a lot with the generate proof here. So kind of coming back to what is this monolithic versus modular, right? We're bringing the point that you can build rollups on top of a monolithic chain. So in all those architecture diagrams, right, if we look back at this, we have Celestia here, but there's no reason you couldn't use Ethereum in place of Celestia here. You can write call data there, and you can do all the things from a node or a light client to read that data back from call data on Ethereum. But the trade-off you're making is that there's fewer types of nodes. So you're just going to have a full node there, and you're going to have a light client there. So you'd have to run a full node, presumably, to get out-of-the-box software to retrieve all of this information to be able to verify your validity proofs or to validate, your transaction in a fraud proof, right? So there's additional overhead to this because of the lack of different node types here. What about more layers? I briefly touched on this, right? We can have an idea of fractal scaling. So I only showed up, to maybe we can say 3 layers, right? But we can have this data layer. We can have an execution layer on top of that. We can have a rollup on top of that. There's no reason we can't have rollups on top of those rollups, right? And so we can have this idea of fractal scaling. Where this kind of comes into play, I mentioned at the start, right? You can have trade-offs in your settlement assurances and your time to settlement, or your, yeah, we'll say time to settlement, right? If I have a, five layers of rollups, right? I can have a very, very fast block time at this very, very high level, but my assumption is that transaction is not truly valid. It doesn't truly have data availability until that layer is bundled into the layer below it, is bundled in the layer below it, and so on and so forth, right? But you can have these softer settlement guarantees and a faster time to finality at a higher layer. And so this is the trade-off space we can have. And this is kind of one of the things modular architectures are going to give us. It's this very, very broad design space where, if we connect it to kind of TradFi, right? When you go make a credit card transaction to go buy a cup of coffee, well, okay, that transaction is not going to be settled for a very long amount of time. You settled between the coffee shop, but that's on credit. When is your credit settled with your credit card provider? When does your credit card provider settle with the local bank? If we are all traveling here to Amsterdam, when does that get settled with, your local bank across wires? When does that end up at the Federal Reserve, right? We have many, many, many layers in the TradFi world. The modular architecture allows us to kind of represent this in the blockchain space, where you can have these trade-offs of, okay, I'm doing a $2 transaction. No, I don't really care if that has, the level of settlement assurances of doing a $1 billion transaction, where I might really, really want to be at the layer one and really guarantee that that transaction is final. So that's one of the things we want to consider. So in this space, what are the current limitations that we're looking at kind of in this modular architecture and design space? And what I'm going to argue is that the developer experience right now is rather poor. If you want to go make one of these things in a modular architecture, right now it's just kind of hard to do. Celestia is trying to make that easier by providing this data layer. But even then, if you want to deploy a rollup on top of Celestia, you need to be able to have an execution layer that knows how to talk to Celestia. It knows how to run a node in Celestia's network. It knows how to generate fraud proofs and write those fraud proofs. It knows how to validate those fraud proofs, or you can go ZK proofs, though I think that might be harder. And then if you want to build another rollup on top of that, well, now you need another rollup that can talk to your execution layer. So we have these many layers of the stack, and quite frankly, they're just not workable out of the box right now. It's hard to go to market with one of these things, and that's why we see, how many rollups do we have there working on it, right? We might have a dozen or more rollups, but that's actually like none when we think about it, right? We want app-specific rollups, or we want general rollups, but we want them all in these different layers where I can say, okay, I can do a generalized transaction rollup here on layer 3, or I can do an app-specific rollup on layer 5, but we're just not there from a developer experience right now. Some ideas. Execution layers are specifically built for settlement, and obviously, Celestia, what I'm working on, my team at Celestia, is building this settlement layer as a sovereign rollup. So this could be thought of as a layer 2, or really thought of as what we currently think of as a layer 1, where we're going to have this execution layer that talks directly to this data layer. But you can design this execution layer that builds for settlement. It doesn't have to be constrained to just that layer. We want to make, coming back to modular software architectures, right? There's no reason we shouldn't be able to make a settlement layer that we can use at all layers of the stack. And so we can actually build out, this 5 layers of the stack using the same piece of software, because what we're actually looking for is something that can produce fraud proofs and something that can verify fraud proofs, right? And we want that same functionality kind of up this whole stack. So app-specific rollups on top of this settlement layer. Again, right now, when we want to make a rollup, everyone's going to think we're making an EVM-compatible rollup, right? We have multiple ZK EVM projects going on there. We have Optimism. We have Arbitrum. They're making, Nitro and Cannon, right, to be able to execute these EVM transactions and validate these fraud proofs. But we can also want app-specific rollups. And maybe embedding the entire, EVM is not what you need to do an app-specific rollup. What you actually want is a constrained set of executions you can make for your specific app, and then the ability to either fraud prove that or ZK prove that. And we can make that much easier by deploying on top of this settlement layer. And then if we bring this to final fruition, right, we can think one-click rollups. If you think about the existing developer flow for someone deploying a website or a cloud-native app, right? You can go to any of the any of the cloud providers, right? And you can, in one click, choose to spin up a Docker container that will scale as large as you possibly want. And all you have to do is write your code, compile it, upload it to their thing, and it will scale as far as you want. There's not really a reason we can't have that same solution in these rollups. And what we looked at here with these kind of block producers and the trust minimized light clients is as we go up these layers, we can accept trade-offs in the centralization here that might not give us the strongest security guarantees we want, but if we're using it for a very small app-specific thing on layer 4, maybe it's okay that, yeah, I'm the only person that runs the block producer environment, or the block producing node for this, but everyone else can run a light client for this if they want, and you're specifically using it for just these transactions on my app. We might think, we're really, really worried about decentralization, but look at the things that we've seen with sanctions on the UI front end for all of our favorite DeFi apps, right? We already have this single point of failure, and yeah, you can fork that and go, but there's no reason if you have a one-click rollup and we have all of our data availability on a base layer that is credibly decentralized, right? How is that any different from forking the UI? And so we can reach this point where we have these one-click rollups, and you can trivially fork it if that gets censored or if you get a fraud proof that shows that the single centralized block producer is doing invalid things in this network. And that can really bring us to a much better developer experience for this whole rollup environment.